Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. So on today's lesson, we're going to be looking at the topic of magnetism. All right, so let's get started. So our main focus on this lesson is depicted as we're going to be looking at the magnets, the type of magnet that they are. We're going to be looking at the magnetic field. We're also going to be looking at the use of compass and magnet, what do we use them for. We're also going to be looking at the prediction of behavior of magnets when we are interacting like poles and unlike poles. We're also going to be finding out what is like poles, what is unlike poles. We're going to be exploring as well the properties of magnetic field lines, okay, which serve as a guideline as to how we should draw magnetic field lines, okay. Lastly, we're going to be looking at the phenomena affected by its magnetic field. All right, but then this is what we need to know by the end of this lesson. Our objective for this lesson, for number one, we need to be able to find to define rather important terms such as magnet and magnetic field. We need to be able, by the end of this lesson, to be able to predict the behavior of magnet when the like and unlike poles are brought together, or rather are interacting with each other. We're also going to have to be able to understand the properties of magnetic field lines, also to be able to explain the difference between geographical North Pole as well as magnetic North Pole. So by the end of this lesson, we should be able to do all these things that are listed over here, which are today's objective of this lesson. All right, so let's begin. What is a magnet, you are asking yourself? So a magnet is an object that has a pair of opposite poles called north as well as south. So below I've put some nice pictures so that you can see that how a magnet looks like. All right, so magnetism is another term that is very important to know before we explore this topic further. Okay, magnetism being an interaction that allows certain kinds of objects, which are called magnetic objects, to exert forces on each other without physically touching each other. Okay. Also, we need to know what a ferromagnetic material is. So we define a ferromagnetic material as a substance that shows spontaneous magnetization. By spontaneous, we mean that it's self-generating or to happen without any external cause. Okay, so this means that the ferromagnetic material has a magnetic field without any external factors being required of it. Okay, so lastly, another important term that we need to know as we explore this topic is magnetic field. Now, a magnetic field is a region in space where a magnet or an object that is made up of a magnetic material will experience a non-contact magnetic force. So this is how like typical bar magnets will look like. Remember, a magnet has to have two poles, a south pole as well as the north pole. If I can take this bar magnet that is shown in our presentation and crush it into tiny pieces, what you'll realize is that each and every tiny piece of that bar magnet is also going to be having a north pole and a south pole. Not only is this north pole there when the bar magnet is whole or is complete, but even every single piece of this crushed magnet is going to have a north pole and a south pole. All right, so that's what I want you to keep in mind. So here are the type of magnet that exist. Now, there's not all of them, but these are commonly used. We have the different shapes depending on the use of it. Remember, we use magnets in our daily life for different purposes. Right, so the first one is a horseshoe magnet because it literally looks like a horseshoe. All right, and the second one is a ring magnet. The other one is a U-shaped magnet. The other one is a bar magnet, and the last one is a cylindrical magnet. All right, now you may be asking yourself, where exactly do we use magnets? Okay, what are the uses of magnets? We use magnets in compasses, we use magnets in small electric motors, we use it in bags, we use it in magnetic cranes, we use it in some toys, and we use it in fridge when we are closing and opening the door, the fridge, the refrigerator doors. Okay, so that the door is able to touch, or rather to close properly and to open. All right, so those are very important aspects of what of the magnets, and where we use them and how useful they are in our daily lives. Right, so how they look like, we have said before in our first slide that a magnet, a typical bar magnet, will have a north pole and the south pole, which are 2 poles. Right, so this is how a bar magnet would look like. But also, it does not just come as a bar magnet alone. Remember, if you put another magnetic object next to it, there's going to be a force that is experienced by these 2 objects towards each other, whether be it that it is a force of attraction or a force of repulsion. Okay, so that means there is a magnetic field that exists. Okay, there's a region in space that exists that is caused by the 2 materials in here. Okay, called the magnetic field. Now, magnetic field can be drawn, okay, in a certain way, and it's a representative of the magnetic field itself. So we use the magnetic field lines to represent the magnetic field. All right, so magnetic field can be represented using magnetic field lines starting from the North Pole and ending in the South Pole, which is always the case. So your magnetic field lines outside of the magnet will always be running from North Pole to South Pole as depicted. That means when drawing the magnetic field lines, which represent the magnetic field, it is important to show with the arrows the direction of the magnetic field. Okay, so direction is very important. Now, depending on the interaction of these materials that you're interacting at the time, whether it is the like poles or the unlike poles that you are interacting in particular bar magnets. Okay, so what happens now, you ask yourself, when the like poles, and by the meaning by like, we mean that they are identical, meaning that the south pole of one bar magnet is interacting with another, okay, pole which is the same as the first one, meaning that the north is interacting with the north pole and the south pole is interacting with another south pole. What type of what type of force is going to be there? Remember, the like poles, the identical poles, they repel. Meaning that the North Pole, if it's interacting with the North Pole of another magnet, there is going to be the force of repulsion between those magnets. But if now the unlike poles, which is the opposite poles, the North Pole interacting with the South Pole of another magnet, that's going to have a force of of attraction. So now we've depicted that interaction in the pictures below. So this is a North Pole of one bar magnet, and there's another a South Pole of another object, the bar magnet. Now that means because they are unlike poles, they're going to do what? There's going to be a force of of attraction between the two. Okay, but if it's like poles, the same, or rather the identical poles, here is the North Pole over here and another North Pole over there, that means they are the same. That means that the force that is there, that is existing between these two bar magnets, is going to be a force of repulsion. They're going to repel one another. They're going to refuse to come to closer together. Okay, now with this analysis, or rather with this explanation of the behavior of the poles, how do we then draw the magnetic field of such a behavior? Okay, so on the first one, we have the north as well as the south pole of different bar magnets. All right, because they are unlike poles that are interacting, there's going to be force of attraction, and that is why the magnetic field lines move from the north pole of one bar magnet to the south pole of the other bar magnet. Okay, rest assured that is always the direction that the magnetic field lines always take. So they have to be strictly moving from the North Pole to the South Pole. Okay, and that means on the North Pole, that is where the magnetic field lines exit or depart, and on the South, the arrows are inward or inward because that is where they are entering. All right. However, if we're looking now at the like poles, whether it be the north interacting with another north pole of different magnets or south to south pole of different magnets, these, remember, we said that there's going to be a force of repulsion between them. All right, so now that is why you see that the magnetic field lines are not touching. Okay, they are not connected, they're not moving from one side to another. However, they are refusing to touch to show that there is a force of what? Of repulsion between the two objects. All right. Direction is still important even in such cases where repulsion takes place. You look at the type of the bar magnet, or rather the poles that are interacting at the time. So in this case, it's north pole of one bar magnet that is interacting with the north pole of another bar magnet. Right. So because with the North Pole, that is where your magnetic field lines exit. They depart from the North Pole. Okay, so your arrows need to be moving outward to show that the direction of what? Of the magnetic field lines. All right. So for us to be able to draw these magnetic field lines, which represent the magnetic field properly, okay, there are certain rules that we need to follow. Okay, so that is why it's important now to look at the general properties of the magnetic lines of force. The first one, magnetic field lines never cross one another. Okay, so there will never be a point where these magnetic field lines have to cross. Therefore, if they are crossing, in your drawing, you've drawn them and they are touching each other, crossing each other, that means we've drawn them wrong. Okay. Number two, magnetic field lines always move from North Pole to South Pole all the time. We always move from the top to down. All right, that is the north being in the northern point of the Earth's rotational of axis. All right, so whether be it that we're not talking in terms of geographical North Pole and the South Pole, we're talking about the bar magnet on the north and the south. Always remember that the magnetic field lines needs to move from the North Pole to the South Pole. All right, and then the third point, which is very much important to take note of, is that magnetic field lines are more concentrated at the poles. Okay, so on the pole themselves, they're going to be more concentrated, but as they are spread in the middle of the bar magnet, then they become less concentrated, and then they become concentrated at the poles again. Okay, so from the North Pole, they are more concentrated. Okay, to the South Pole where they are entering, they are more concentrated. However, in the middle, okay, that's where they are spread far apart and they become less concentrated as compared to the what? To the poles. So we mean by that is that the forces of attraction and repulsion, okay, depending on the type of the bar magnet that are interacting. Now, the forces of attraction are more concentrated at the poles, because these magnetic field lines tend to be more concentrated at the poles and less concentrated in the center of the magnet. All right, and then the fourth point will be their density decreases with an increasing distance between the poles. What does that mean? That it means that as you put these magnets that are interacting with each other far apart, that means that the density is going to increase. And what do we mean by that? We mean that the number of the magnetic field lines become less, okay, in the middle of the bar magnet, and they become more concentrated at the poles themselves. And that is why that we regard that for the density to decrease in the middle as there's an increase in the distance between the two interacting bar magnets, okay, from the poles. All right, so as you increase the distance, the density of the magnetic field strength decreases as well. All right. And then they are considered to have direction as if they are flowing. However, they are not really flowing, though no actual movement occurs. So it's considered to have this flow that is happening between the interacting bar magnets. However, there's no actual movement that occurs. You may ask yourself, why is that? It's because the magnetic field lines are continuous in nature. Okay, meaning that they flow from the South Pole to the North Pole, but that happens within the material. Okay, and what we are able to draw is to draw what happens on the outside. Okay, so they flow from the South Pole to the North Pole, but that happens within the material. Okay, and then they continue then to flow from the North Pole to the South Pole, and now outside of the magnet. And what we tend to draw is to draw the magnetic field lines outside of the magnet. That is why we are so focused on saying they move, or rather they are always moving from where? From North Pole to the South Pole, because we never consider to draw the magnetic field lines within the material. We always focus on what happens on the outside as we are looking at the interaction of this bar magnet with another object. So hence it makes sense that we draw the magnetic field lines that happen, or rather the magnetic field that happens on the outside. All right, so these are important to take note of, okay, when drawing your magnetic field lines, so as to draw them correctly, okay, and so as to get the full marks. Right. Now, not only there is like a magnetic field only in bar magnets, but also there is like what? An Earth's magnetic field. Earth has a magnetic field, you may ask yourself. Yes, it does have a magnetic field, but here's why. It's because the Earth consists mainly on its core, consisting of iron. And we do know that iron is a magnetic material. So if it is a magnetic material, it means that it produces the magnetic field, all right, which is both inside and outside of the Earth's surface, right? Now, if the Earth now is made consistently on its core with the iron, and iron being a magnetic material, meaning that it will produce the Earth's magnetic field, which is both inside and outside of the Earth's surface. That means that the Earth will have now two magnetic, and I want to highlight magnetic, okay? It has two magnetic poles, all right? It has the North Pole, okay? In this case, we call it a magnetic North Pole and a magnetic South Pole, okay? Just like the one you'll observe in a bar magnet, okay? Why is there now a magnetic North Pole and a magnetic South Pole? It is due to the fact that there is iron. There's an iron material that is there at the core of the Earth, and it's producing a magnetic field. Okay, hence the magnetic North Pole and hence the magnetic South Pole, just like in bar magnets. Okay, but now I just put a picture of a compass there. All right, I want you to see the compass pointing at the North Pole, but look at where the North Pole is at according to our compass, and look at where the South Pole is at. So these are what we refer to as the magnetic North Pole and the magnetic South Pole on this dot, because we are looking at the compass itself, right? However, geographically, okay, according to the Earth's rotation of axis, this is where the North Pole is at, and this is where the South Pole is at. That means even though the Earth does have these two magnetic North Pole and South Pole, meaning that if we're saying two magnetic North Pole, we mean there's a North Pole and a South Pole. All right. And then we got the geographically, this is the one, this is the North Pole, and this is the South Pole in here. That means these two, the geographic North Pole and the magnetic North Pole, are not corresponding with one another. There's a certain degree or a certain distance that it differs with. All right, let's explore that. Now, before we even explore that, the compass needle points on the Earth's magnetic North Pole. The compass needle, here's our compass needle, it is pointing at the Earth's magnetic North Pole. Remember, this is our magnetic North Pole, and this is our geographic North Pole. This is our this is our geographical pole, and this is our magnetic South Pole. Okay, so where the compass needles is pointing, it is pointing the magnetic poles. Okay. What is it that we need to also know about the Earth's magnetic field? Okay, in addition to these magnetic poles, we said that the Earth also have two geographical poles. Okay, these are on the Earth's axis of rotation. Okay, where you'll just locate it, because now the Earth, we know the Earth that is moving steadily around axis of rotation. Okay, knowing that the north is at the top and the south is at the bottom. Okay, however, this does not align with our magnetic north and our magnetic south. Okay, here's why. Because these are the points around which the Earth rotates. Okay, now the geographical North Pole is also called the true north. It's the true north because that's where geographically we will locate the north. Okay, but due to the ion that is there incorporated in the Earth's core, then we have the magnetic north. Okay, not corresponding with our geographical north, which we call to be true north, but it is there. Okay, then the magnetic poles of the Earth do not correspond exactly to the geographical poles. And how do they differ? The geographical North Pole is about 11.5 degrees away from the direction of the magnetic North Pole. All right? And here's a nice picture that is showing that. Our true north, remember we said this is our geographical North Pole. And we refer to it as what? We refer to it as a true north. Okay? Where the point of axis of this Earth, okay, is rotating. All right, and then here's our magnetic north, and we said that it is away from the magnetic north to the true north by what? By 11.5 degrees. All right, so when we say these do not correspond, we mean exactly that the compass will point on the magnetic north, meaning that the compass needles will point on the magnetic north. Why would the compass point there? It's because of the presence of the iron core that is there in the core of the Earth. Okay, because the iron is what? It's a magnetic material. However, before we even go from this picture, I want you to look at the magnetic field lines. The magnetic field that is there. Remember, the magnetic field is represented using what? Using the lines. Direction is important, okay? From the North Pole to the South Pole. All right? From the North Pole all the time to the South Pole, because that happened outside of the what? Of the magnet. Remember, we said they are continuous as well, meaning that they're always going to go in here from the South Pole to the North Pole, but that is happening within the material. And then we draw what happens on the outside again. All right. So, but now, what is the phenomena that is affected by the Earth's magnetic field? Yes, we know now there is an Earth's magnetic field, meaning that the Earth itself does have a magnetic field all around the Earth. So the Earth has the magnetic field that is there. Firstly, what do we call this magnetic field that is around the Earth? We refer to it as a magnetosphere. Okay, remember, this magnetic field that we refer to, we cannot see it with our naked eye. We cannot see it, but we know its behavior. Because now we know how two materials will behave when the North Pole and another North Pole are brought to each other. We know that they're going to repel. So it only makes sense that now we need to draw the lines to envision what kind of force is happening to demonstrate this force of what? Of repulsion. If now unlike poles are what? Interacting with each other. Your North Pole and your South Pole interacting with each other. Okay. Then there's a force of attraction in there. And then we need to draw that force of attraction. We need to see that, oh, okay, because these are what? Are attracting, we need to show it by the magnetic field lines. All right. However, they are invisible. All right, we draw the line so that we can be able to best explain the force of attraction behind it and the force of repulsion behind it. So that is why we say the invisible magnetic field around the Earth is therefore called the what? The magnetosphere. That just has to be a name for it. So harmful particles and gases from space, they are constantly heading towards the Earth. So in space, remember, Earth is not the only the one that's there. However, there are harmful particles that are always heading towards the Earth all the time. All right. So it can be particles and gases that are constantly moving towards the Earth from space. All right. However, because of the magnetic field, okay. However, because of the magnetic field, most of them are deflected. When something is being deflected, it means that it bounces off. It is not able to penetrate through the Earth. So here's our Earth, okay? Harmful particles head towards the Earth all the time. It could be the particles, it could be the gas particles as well, okay? They are always charged, they are always coming to the planet Earth all the time. However, because of this magnetic field, which we refer to as a magnetosphere, which is around the Earth, it is protecting what? The Earth by doing what? By deflecting. So as these particles come, they just bounce and change direction. They are being deflected and change direction around the Earth. And they are not able to penetrate through and cause harm within the planet Earth, because now we live inside this planet. All right. So the magnetosphere allows for these electrically charged incoming particles to be bounced off the Earth's magnetic field. All right. That is how the magnetic field protects the beautiful planet Earth. All right. So, however, in some areas, okay, deflection does not happen, especially at the poles. And then when deflection does not happen, this bouncing off of these charged particles heading from space, heading from the sun, in some areas, when the deflection does not happen, it means, oh, a massive blow for the planet Earth. Okay. So serious things happen inside the planet. Okay, it could be the cut off networks, but some destruction, some disturbances happen. Okay, but we're going to find out how do those distractions or interruptances happen inside the planet Earth. Okay, so when they are not, these particles, charged particles from space heading towards the Earth, are not deflected, okay, they result in something that we refer to as the red and the green lights, okay, that's then stretch across a large part of the sky, and that we refer to as an aurora. All right, so we also refer them to be, depending on where exactly, which pole was affected at the time. It could be that these harmful particles from space just crashed onto the North Pole, or just they just got into the North Pole, or they got into the South Pole. What really happens then? Okay, rather, what really happens, and how can we tell that, oh, okay, these ones happen through what? The North Pole, and these ones happen through the South Pole. Okay, so we refer to them as the Northern Lights because it happens at the on the North Pole, and then the one that are happening on the South Pole we refer to as the Southern Lights. But if we don't want to use that terminology, for the Northern Lights we use Aurora Borealis, and then for the Southern Lights we can also refer to them as what? As Aurora Australis. Okay, so there's just big, massive red and green light that stretch across a large part in the sky. All right. So this is how they would look like. So this is a northern lights, or rather aurora borealis, okay, in the North Pole. And this will be the aurora australis, okay, or we refer to them as what? As the southern lights, okay. So remember, we said that it does happen that the charged particles from space are not deflected back. They do get into the North Pole. They do get into the South Pole. What is it that happens? Okay, so let's talk about, we did discuss what? The auroras, all right? The aurora borealis and aurora australis, all right? But there's also something that we call geomagnetic storm, okay? So these are then what? Particles that are charged from the sun heading towards the earth. Oh, dear earth. Now it's trying to cover itself up. However, covering itself up by using the magnetosphere, which is the magnetic field around the earth. But how do then these storms happen when there is a magnetosphere around the earth? Okay, what transpires when a geomagnetic storm happens? Okay, in detail, here's a step-by-step. Now, what happens is the sun sometimes ejects a large bubble of material that is made up of protons and electrons. And we will remember that these are charged particles because protons are positively charged and electrons are negatively charged. So it releases this huge bubble, okay, a large bubble of material, okay, made up of protons and electrons, okay. So this bubble then travels straight towards the earth, okay, and instead of being deflected, what happens that it joins, this bubble then joins up with the Earth's magnetic field, okay, resulting in this big amount of energy being released, okay, at the atmosphere, causing a geomagnetic storm. All right, so these storms then they cause fast changing inside the Earth's magnetosphere, which affect then the electric and the magnetic system inside the earth. You'll find that there's going to be cell phone network problems and other electronic systems that are being interrupted due to this geomagnetic storm. So you have the sun ejecting a large bubble, which is mainly made of what? Of protons and electrons, which we consider to be charged particles. And then this bubble material is then travels straight towards the earth. Instead of the earth now, or the magnetosphere bouncing this large bubble, it then the bubble is able to get itself joined up in the Earth's magnetic field, resulting in this big explosion, or rather the release of the big amount of energy in the Earth's atmosphere, causing a storm. So storms do affect operations within the Earth, because now it means that our protective layer, our protective magnetosphere has now been disrupted, okay? Meaning that because there was a disruption at the security gate, there's going to be disruption inside the Earth, okay? So that is how it is shown. So here's the sun releasing a bubble and heading towards what? Heading towards the earth, all right? Not only is that the only phenomenon that happens, or rather the auroras and geomagnetic storms, but they also solar winds, okay? How do solar winds happen, all right? So let's look at the picture first so that you're able to understand it nicely. There's your earth, nicely there. Here is your sun. There's a sun there. Here's the earth, and there is the magnetosphere, which is just the magnetic field around the earth, okay? Now, the sun is releasing these ionized gas particles, and they are blowing in the direction of what? Or rather towards the earth, okay? And solar winds happen at a very high speed, approximately 400 kilometers per hour, towards the what? The earth, right? And then what is it that happens? Then happens due to these ionized particles, charged gas particles from the sun, okay? moving at the speed of about 400 kilometers per hour towards the Earth. That means that the strength of the wind, how fast, okay, the strength of this wind will depend then on the intensity of the sun. Okay, makes sense. Also, the Earth's magnetic field then shields it from the solar winds. Okay, here is the magnetosphere, which is the magnetic field around the Earth. The Earth's magnetic field shielded from these solar winds. Okay, when the wind hits the Earth's magnetic field, it is deflected, meaning that it is able to just bounce back in the direction it came from. All right, and then the Earth's magnetic field is therefore important in protecting, okay, in protecting the Earth from what? The harmful particles from space that are constantly heading towards the what? The Earth. Okay, so you've got your ionized charged particles blowing in the direction of the Earth from the sun, moving at a very high speed. Okay, then the Earth's magnetic field then is able to shield the Earth. It's protecting. Again, another word that you can use for shielding. It's protecting the Earth from these solar winds, which are mainly composed of the what? The gas particles. Okay, that are able to do also, not only that, it is able to strip, okay, the ozone layer. Okay, making us to be vulnerable to the what? To the UV rays. Okay, so because of these charged gas particles that are constantly moving from the sun towards the planet Earth. Okay, so the great job that the magnetic field around the Earth, or rather the magnetosphere, is able to do is that it deflects these charged ion particles away from the sun, okay, in the direction it came from. Okay, now, because now we have learned all of this information in magnetism, okay, we know what is a magnet, we know what magnetism is, we know what is a ferromagnetic material, and we do know what is a magnetic field. Okay, not only that, we also explored the general properties or rules that we need to follow when drawing the what? The magnetic field. We did it not end there. We also explored the Earth's magnetic field, which is magnetosphere. We looked at the phenomenon of the effect of having the magnetic field, Earth's magnetic field, or rather having magnetic field lines around the Earth, which we refer to as what? A magnetosphere. All right, so with all of that, with all the information that we've learned, we need to then be able to analyze whatever question that is being brought to us, whether it comes in a form of a multiple choice question, which is what we're going to first explore, and then we're going to be looking at the long questions. All right, so before we even get into the long questions, let's first get the skill. It is important to learn the skill of answering your multiple choice question. You just don't say, which alphabet do I like better? Okay, I feel like I like D more, and then you choose a D, and then you look at another question, which one do I feel I like this time? Oh, I feel like it. No, we have to look at the question. We need to understand what the question wants us to do, and then be able to identify the two distractors. So mostly, you are given 4 possible answers as possible answers to the question. So now they're not answers, okay? So possible answers to the question. And then there is 2, those ones are distracting you, meaning that they have no business or have nothing to do with the question. And then you have the one that is similar to the answer, and then you have your correct answer. Okay, so let me repeat that again. You've got your 4 possible answers, okay, for that specific question. The 2 ones are distracting you. We call them your distractors. The one here is similar to your answer, but there's something wrong with it. It's not the answer, okay? And then we have the last one, which is your answer, okay? So how do you then gain the skill? In you reading the topic, is important to read it correctly, analyze it, and then be able to say which one does not belong here, which one cannot be the answer first, so that you leave the 2 options, so that you differentiate between the correct one and the one that is similar to the correct one. All right, so the first multiple choice question, so MCQ standing for multiple choice question. So the first one is saying a bar magnet is cut along the dotted line shown below into two pieces marked A and B. Right. So at first it was a bar magnet that is complete, and then we decided to cut it. Remember what we had said about a bar magnet that has been crushed. So any magnet, if it's like this, it will have two poles. Okay, it is complete. So there will be your north pole and there will be your south pole. Right. However, if we crush it into tiny pieces, we had said that every tiny piece will have two poles as well, which is your north pole as well as your what? Your south pole. All right. So on picture A, or rather the first diagram, there is a whole magnet, meaning that it is not crushed as yet, it is not cut as yet. And then on the second diagram, now the bar magnet is being splitted or cut into two pieces. Okay, don't forget that in each piece now we have the north pole and the south pole, and a north pole and the south pole. Now the statement continues to say, a learner tries to reassemble the magnet by bringing the cut sections of the magnet close to each other. All right, which one of the following will happen when the two cut sections are brought close to each other? Okay, so remember, because there were it was just one bar magnet. So over here there was a north and a south, and because each piece has to have, okay, two poles, that means if this one is a south pole, this one is a north pole. If this one is a north pole, this one is a what? Is a south pole. Okay, now which one of the following will happen when the two cut sections are brought close to each other? All right, the cut sections A and B will, option A is saying repel, option B is saying attract, option C is saying attract and then repel. Okay, is there such a thing? Attracting and then? Nah, it can never. So this is my destruction. Okay, exert no force on each other. No, there has to be a force between the two objects. So no. But now, is it a repulsion or is it an attract? That's the question. Because now these are unlike, meaning they are not the same. Okay, two different. Okay, that means they will attract, because we had said unlike poles attract, like poles repel. So the correct answer over here is what? It is B. Okay, let's look at 1.2, still on multiple choice question. Astronauts in space are at risk of being irradiated by solar winds because, so in space the astronauts are being at risk of being irradiated by solar winds, right? They are telling us. Why? Is it because they are inside the magnetosphere? But how can they be inside? Because here is my planet Earth, and what I will refer to as, okay, this is a terrible diagram. Let's draw again. And I want it to be big because remember the rule saying the magnetic fault lines should never cross. So really they should never cross. Okay. Right. Direction. All right. So let's say that will mean that over here I've got my north pole, and over here I've got my south pole. Remember, they're always going to move from the north pole to the south pole. I'm trying to analyze this question together. Astronauts are outside, they're over here. They're outside the Earth. They're outside the planets, because the Earth is amongst the other 9 planets that are there in space. So it cannot be inside the magnetosphere because you are not inside the planet Earth. So that one is a distraction. Okay? Okay, because they are inside the Earth's gravitation. Gravitational field happens inside the Earth, and the astronauts are over here. So this is also a what? A distraction. Okay? Option C, outside the magnetosphere. Okay, yes, astronauts are outside the magnetosphere, so that could be an answer. All right, and then outside the Earth's gravitational field. Similar, but it's not the answer. So the correct answer over here is that they're outside the magnetosphere. So that is why. Okay, remember the magnetosphere serves as a protection to the Earth. So now when you are outside of it, you are at risk of being irradiated because the solar winds are going to come and blow and have, because the solar winds are made up of these charged particles from space and from the sun. Okay, so astronauts, because they are over here, they are being at risk of being irradiated by these harmful charged particles because they're of what? They are outside the magnetosphere, because here is the magnetosphere over here. All right. 1.3, still on multiple choice question. Which one of the following material is attracted by a magnet? This takes us back into the content of grade 10, okay, where we learned how can we tell that this material is magnetic. Okay, so what will the experiment that we'll do, we'll take a bar magnet and we'll place it next to this material, any material that you're trying to check whether it is magnetic or not. Okay, so we'll take a magnet and put it next to the rubber, and we'll take it we'll put it next to the string, next to the metal rod, next to the wood. Okay, so as to check which one or which type of which material is magnetic. Okay, so this is just basically grade 10 content. Okay, which one of the following materials will be attracted by a magnet? A piece of rubber, it's a definite no. A string, it depends what it's made up of. So it's similar to the answer. Okay, so we're going to leave it like that. Metal rod, we know metals to be magnetic, so this is a good answer. All right, and then wood, it's a total no. So we find our destructors, we find our correct answer. Correct answer is what? It's our metal rod. All right. And then we get on to the long question. Question 5, taken from the past question papers. I think it's 2019 from the Eastern Cape. And then it says, 5.1, define the term magnetic field for 2 marks. Remember, with definitions, it's 2 marks or nothing. Okay? And you cannot be defining it partially right for you to be getting 1 mark, but you need to define it entirely correct. Okay, meaning that when we say it's 2 marks or nothing, you have to define it correctly, and you get awarded 2 marks. You write it partially correct, and then there's no mark. Okay, so what is a magnetic field? It is a region in space where a magnet or material that is made up of magnetic material, okay, or ferromagnetic material will experience what? A magnetic force. Okay, so a region in space where a magnet or a ferromagnetic material will experience a force. A force. All right. So that is our 2 marks. That's how simple you get your 2 marks. 5.2. Name the instrument that is used to determine the direction of the magnetic field. Okay, what is it that we use? What instrument? We use the compass. Okay, I know you got that right as well. Moving right along, name 3 properties of magnetic field lines. What are the properties? What are the rules? What are the properties that you should stick to when you're drawing magnetic field lines? First one, magnetic field lines never cross. Okay, that's the first one. Number 2, magnetic fault lines always run from North Pole to the South Pole outside of the material. So, magnetic fault lines always run from North Pole to South Pole outside of the material. Okay, the last one. They are continuous. Magnetic fault lines are continuous. Okay. Let me just write over here because I get distracted over there. They are continuous. Right. So this time they were asking for 3, but remember we've discussed way more than 3. Okay, so that you can write the ones that you like. Okay. And then there's an interesting diagram which is accompanied by a statement that is 5.4. In the diagram below, the Earth's magnetic field. Okay. In the diagram below, the Earth's magnetic field is represented by the magnetic fault lines. Here are the lines. We can see them. All right. The Earth is viewed as having a bar magnet at its center. All right. 5.4.1. And then we analyzed. Give yourself time to analyze the diagram. Give yourself time to look at the diagram. All right. What magnetic pole, meaning that is it north or south? What magnetic pole does number 1 indicate? Okay, so you have to look at the arrows because they're telling you about the direction. All right, the direction of the magnetic field. Okay, where is it going? And then you have to remember that, okay, magnetic field, or the magnetic field lines always move from the North Pole, okay, to the South Pole, meaning that they are exiting from the North Pole and they are entering at the South Pole. Now, by reminding yourself of that information, and then you look at what is given to you. Now, how the magnetic field lines are moving, they are moving in this direction. And I'm saying this direction because I'm observing the arrows. Okay, so it's moving upward. Okay, maybe my arrow is not that nice. Let me just write it clearly. Okay, like that. So that means number 2 on that bar magnet is what? My North Pole. And number 1 is my what? Is my South Pole. All right. So the correct answer over here is what? Is South Pole. We are still continuing with the same question and say 5.4.2, differentiate. Okay. When the question says differentiate, please differentiate. You can even do it using a table to make it simpler. Or you can first write the geographic North Pole definition and then write the magnetic North Pole definition. Okay, the simpler way is for us to draw a table because we want to see this difference between the geographic North Pole and the magnetic North Pole. So you can simply do this. Okay, and then on the first one, we say it's a geographical North Pole. And then on the second one, you can say, okay, this one is a magnetic North Pole. Okay, so a geographical North Pole is what? This is just the northern point of the what? Of the Earth's axis of rotation. Is the northern point of the Earth's axis of rotation. All right, the northern point. And then the magnetic point is just the direction of the North Pole in the compass. okay, where the compass, the needles will point. So it is just the direction of the north pole in which the compass needle, okay, points. Okay, so that is how simply you differentiate it. So table, you can see that it's a geographical pole, the first one we looked at, and the magnetic pole, the second one that we looked at. Okay, 5.5 is here, and it's saying write down the names of two phenomena that is affected by the Earth's magnetic field. What is it that is affected by or affected by the Earth's magnetic field? Number one, we spoke in terms of geomagnetic storms. Geomagnetic storms. We spoke of solar winds. We spoke of auroras. Okay, but they said two. So any two, all right? Any two that you like. Okay. 5.6, which is our last question, it says explain how the Earth's magnetic field provides protection from solar winds. Okay, how does the Earth, it's the how in it. How does the Earth's magnetic field provides protection from the solar wind? Okay, so the Earth's magnetic field Earth's magnetic field deflects. Remember what we said about deflecting? It deflects the solar winds. Okay, this is very much important because now it just bounces them off the surface of the Earth. Okay, it deflects the solar wind. Okay, and then this solar wind is usually which is made of particles. Let's say harmful particles to be precise. Harmful charged particles. Yes, harmful charged particles. Okay, that strip away the ozone layer. Okay, what does ozone layer do? Now, ozone layer is known, it protects the Earth from the harmful UV rays. Okay, so that's how the Earth's magnetic field is able to protect the Earth from these solar winds, mainly made of the harmful charged particles heading from the space towards the Earth. Okay, when we know that these harmful particles will strip away our ozone layer, okay, making us to be more susceptible or to be vulnerable to what? To UV rays. All right. So that's how you analyze the question. That is how you look at the question, be it a multiple choice question or a long question. Please put the information that you've learned, okay, into practice. Analyze the question. Look at the diagram if it's given to you, so that you are able to make an informed decision on how you should answer. Okay. Now, here is the work that I would like you to do for me. Okay, so it is question 7, very similar to what we've just done today. Also, this is your chance now to work as well to see if you understood what we spoke about today or you did not. Okay, if you did not, it's okay to start afresh, go through what we spoke about, and then go through the questions again. All right, this is taken from a past question paper as a question 7. Okay, it's saying starts on a new page. Rather now, it's saying a bar magnet A, all right, is placed as shown in the diagram below. Right, so it's just a full bar magnet. It's got 2 poles, right? And then 7.1 is saying define the term magnetic field. Remember the terms that we started off our lesson with? We said we cannot go any further. We can't keep referring to a magnetic field if we do not know or if we do not understand what a magnetic field is. All right, and then 7.2, that is for 2 marks. Before I move on to 7.2, that is for 2 marks, meaning that please write your definitions in full, because for you to be awarded that 2 marks, you have to define fully, okay? Or if you did not define fully, then you get nothing. So we 1 marks, all right? 7.2, give 2 properties of magnetic field lines. Oh my God, we spoke about a lot of the magnetic properties, but this question just wants you to remember 2. Only 2 for you to be awarded that 2 marks. All right, and then moving right along, still the same question, but now we're on 7.3. It says sketch the magnetic field pattern around a bar magnet A. Ooh, around bar magnet A, not A and B, only A. Remember, A has got the 2 poles, the north pole and the south pole, as you can see. Now, always remember the properties of how to draw the magnetic field lines, which depict the pattern of what will happen in magnet A. All right, that is 3 marks. Direction is important. Making sure your lines are not crossing is important. Making the magnetic field lines to be more concentrated at the poles and less concentrated in the center of the magnet is very important. All right. A second bar magnet, B, is then placed near A, as shown in the diagram. So there's an introduction of magnet B, which also has a north pole and the south pole. Okay. And then 7.4 is saying, what kind of force does each magnet experience due to the other magnet? So A will experience what kind of force due to B, and what will B experience? What type of force will B experience due to what? Due to A. What do you have to read between? So you need to look at the association, or rather the interaction between the poles that are closer to each other. Okay, are they like poles or are they unlike poles? Okay, remember what we said, like poles repel, unlike poles they're more loving, they are attracting each other. Okay, so is south and north like or unlike? You can answer that for me. Okay, so you can write down attraction or repulsion. So that is how you analyze as well. And then 7.5 goes on to say, define the term magnet. What is a magnet? Yes, we're talking about magnetic field. Yes, we're talking about magnetic field line. Yes, we're talking about the magnet in magnetism and so on. But what is a magnet? Because we cannot go any further, any step further, without even understanding the basic concepts. Okay. 7.6, write down 2 examples of ferromagnetic materials. Okay. Remember, we said they are spontaneous. They don't need external factors, okay, for them to behave otherwise. So what are the examples of ferromagnetic materials? Okay. For 12 marks. So if you can get the 12 marks. Boom, 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 boom. So I'm going to end today's lesson by a quote of the day. This is by Virgil Abloh. It says, they succeed because they think they can. They can conquer who believe they can. They succeed because they think they can. So it's all in your thoughts. And they conquer because they believe they can. So what is it that you're believing in today? Are you believing in yourself? What do you think about your abilities? Do you think you can do this? Do you think you can be able to pass grade 11? I think you can. So what is it that you're feeding your brain is going to be the outcome. You feed it negativity, negativity is going to be blowing out. You feed it positivity, yes, I can. Yes, I believe I can conquer. Yes, I think I can make it. Yes, I think I can succeed. Should be the terminology in your mouth. Should be what you speak to yourself. Should be what you proclaim to yourself. Have a wonderful day. I hope you had a wonderful time with me as we were sharing magnetism together. Have a wonderful afternoon. Bye-bye.